In 2024, a century-old math problem was solved, one whose simple beauty even led to the marriage of two mathematicians. But the more you learn about it, the more miraculous it seems that this was even possible. The number of options that had to be searched far exceeds the number of particles in the universe, and the final proof is so long that no one can even attempt to read it. In this video, I'm going to show you how a simple idea led to a century-long history of geometric questions, how we became stuck on the very last step, and how we finally broke through with a combination of ingenuity and a stroke of luck.
Let's hope everything works out. And sometimes you're lucky. Just try it and see how far you get.
This is the story of the empty hexagon problem. In the early 1930s, Esther Klein, a young Hungarian mathematician, was working on a much simpler puzzle that would later give rise to the empty hexagon problem. She was studying points in the 2D plane, where no 3 points are in a line. She asked how many points it would take to guarantee that 4 of them make a convex quadrilateral, a 4-sided shape with no dents. Very quickly, she had the answer: 5. In 1933, Klein sent her work to Paul Erdős and George Szekeres, who had been working together on related questions. They immediately recognized the significance of her work. Szekeres remarked in a memoir that there was a feeling of excitement that a new type of geometrical problem had emerged, which they were only too eager to solve. So how did Klein prove that any 5 points in the plane produce a convex quadrilateral? She broke apart the problem into 3 cases based on the shapes involved. If all 5 points form a convex pentagon, then any 4 of them form a convex quadrilateral. If there's 1 point on the inside, the 4 points on the outside form a convex quadrilateral. And if 2 points are on the inside, connect them with these 2 points on the outside. This again forms a convex quadrilateral. Any set of 5 points where no 3 are in a line falls into one of these 3 cases, which each produce convex quadrilaterals. And we can show 4 points isn't enough with this counterexample. Here are 4 points with no convex quadrilaterals. Any 4-sided shape has a dent. The beauty of Klein's work particularly caught the eye of Szekeres. After a few years, the problem actually led to their marriage. Erdős later nicknamed it the happy ending problem. But the happy ending problem also led to broader questions that served as stepping stones to the empty hexagon problem. Erdős and Szekeres wondered whether there's always a finite number of points that guarantees a convex pentagon, hexagon, and beyond. In 1935, they showed that, indeed, adding enough points to the plane eventually produces convex shapes with any number of sides. But finding how many points are needed was a different question. Some cases were known. For triangles, any 3 points form a triangle, and all triangles are convex. For quadrilaterals, we just saw you need 5 points. However, it would take until 2006 to find the number of points needed to guarantee convex pentagons and hexagons, 9 and 17. The proofs were growing complex, and even to this day, nobody has found the number for any shape with more than 6 sides. But at the same time, a new question had been brewing in the mathematical community, one that was gaining attention because this question was heading toward a clear and final resolution. This new problem is about empty convex polygons that don't contain any other points. Now we want to know the number of points needed to guarantee an empty convex shape, whereas before we only needed the shape to be convex. What made this new question so exciting is that by 1983, we had already solved it for shapes with every number of sides more than 6. It's infinity. No number of points ever guarantees a convex shape with more than 6 sides. Joe Horton, a Canadian professor of computer science, proved this by finding an infinitely scalable pattern of points where any empty convex polygon has at most 6 sides.
Take any set of points. You can shrink the x-axis so that the points all come together and they all form almost a vertical line.
This is what it looks like. It starts with 2 points. Then those are copied and shifted up and to the right. Then everything is copied again and shifted up and to the right again.
You make one copy and push them together, and then you make one copy of the result, and then you push those together. Make one copy of the result and push those together.
You can keep copying all the points and shifting up and to the right as many times as you'd like. Horton designed the process in a clever way where the coordinates of the points are such that there will never be any empty polygons with more than 6 sides. An empty hexagon can form, but there's just no way to squeeze in any more points to the shape without containing another point. So we knew the empty polygon numbers for shapes with more than 6 sides, and in addition, we knew the empty polygon numbers for the simpler cases of triangles, quadrilaterals, and pentagons. The answers were 3, 5, and 10. As of 1983, the only question remaining was, what is the empty hexagon number? How many points do you need in the 2D plane before there will necessarily be an empty hexagon? But there were 4 crucial problems that meant finding the empty hexagon number could only be made possible by an incredible stroke of luck. Problem number 1 is, for a set of arbitrarily placed points in the plane, there is an uncountably infinite number of ways the points could be laid out. Any procedural search through all possibilities would somehow have to take into account every single arrangement. Now, Esther Klein's proof accomplishes this with 3 simple categories. But that's a relatively tame example. For much more complicated ones, it's not at all clear how you could sort the infinite possibilities into a finite number of cases.
There are so many ways of putting points in the plane that you need to kind of abstract it to start reasoning about it. And so,
in the late 20th century, famous computer scientist Donald Knuth had been playing around with a way of characterizing triples of points by their clockwise or counterclockwise orientation. For example, going from point A to point B to point C here, we're turning to the right, or clockwise. And in this example, going from point X to point Y to point Z, we turn to the left, or counterclockwise. So how does this help manage the infinite possibilities of where the points could be? What kinds of geometrical information can we deduce from knowing the clockwise or counterclockwise orientations of sequences of 3 points? Well, one property we can assess is convexity. Notice that as you move around the outside of a convex polygon, you always turn in the same direction. Any turn in the opposite direction from the previous turn makes the polygon sort of fold in on itself, creating a dent. So let's try to use this fact to reconstruct Esther Klein's proof that 5 points guarantee a convex quadrilateral. Label the points A, B, C, D, and E. To reason about all possible shapes these points could make, take each subset of 3 points and assign an orientation, clockwise or counterclockwise. There are 10 such subsets, each either clockwise or counterclockwise, meaning 1024 possible versions of this table, each one corresponding to a possible arrangement of points. We want to show that all of them produce at least one convex quadrilateral. Note that this table only includes the unordered sets of 3 points. For example, the sequence BCA doesn't get its own row, only ABC. But that's actually enough information for us. Since ABC goes clockwise, then BCA also goes clockwise. Moreover, we could infer that CBA goes counterclockwise. Using that knowledge, let's check if the quadrilateral formed by A, B, C, and D is convex, using just the table of orientations. The table says ABC goes clockwise. Now look at the next 3 points, BCD, also clockwise. Same for CDA. However, DAB goes counterclockwise, which is the opposite direction, meaning the quadrilateral formed by A, B, C, and D is not convex. But if we instead check A, B, C, and E, we would get 4 clockwise turns, confirming that A, B, C, E is a convex quadrilateral. That means this set of orientations produces a convex quadrilateral. This was just one orientation set, but to prove the result of the happy ending problem, we need convex quadrilaterals in every possible orientation set. So let's do some more for good measure. With these orientations, A, C, E, and D make a convex quadrilateral with 4 counterclockwise turns. And with this other set of orientations, B, C, D, and E make a convex quadrilateral with 4 clockwise turns. If we find that every possible set of orientations has a sequence of 4 turns in the same direction, then every 5 points in the plane produce a convex quadrilateral. Now, a quick disclaimer. As I've currently presented it, this method only almost entirely works. The general idea is correct, but there's a slight problem that makes the proof not fully succeed, and in reality, you need to make some slight modifications to make it work out. I'll leave figuring out why as a challenge to the viewers. But the bottom line is, we can express the property of convexity using only these orientation variables. So what else can they do? Can they help with empty polygons? Well, amazingly, they can. Here's a way to detect when a convex polygon contains another point. When moving clockwise around the shape, a point inside is always in a clockwise direction as well. If a point is outside the shape, there's an edge where you would have to turn counterclockwise to get there. If every other point is outside, we know the polygon is empty.
Yeah, it never occurred to me that you could use them in geometry. Yeah, it immediately motivated me to reach out to people and see if we could work out on something.
Somehow, there was a simple way to reason about a geometry problem with infinite degrees of freedom using a finite number of discrete cases. This solved problem number 1. Throughout all these years, George Szekeres kept a close eye on all of this. He had lived a long and remarkable life. Shortly after their marriage over the happy ending problem in 1937, he and his wife Esther were forced to flee from the Nazi regime, leaving their hometown of Budapest. Szekeres took a job as a leather chemist in Shanghai, where he and his Jewish family lived out the duration of World War II, the Japanese occupation, and the Chinese Communist Revolution. Somehow managing to avoid starvation, they made it to Australia, where George had a flourishing career as a professor at the University of New South Wales. But even after his retirement in 1975, he was still hungry to contribute to the mathematics that found him the love of his life. Excited about the developing techniques, he designed a computer program with his colleague Lindsay Peters that used orientation variables to find that the convex hexagon number is 17. In 2005, they wrote a paper with their findings. Sadly, George and Esther Szekeres both passed away before the paper was published in 2006. Their deaths were less than an hour apart. Nonetheless, news of the computerized method was spreading, and mathematicians wanted to apply it to the empty hexagon problem. But the program by Szekeres and Peters to find the convex hexagon number took 1,500 CPU hours to run. That's 62.5 days. The same approach would be infeasible for finding the empty hexagon number, and that's because of problem number 2. With 3 points, they can move to different locations, but ultimately they end up forming a triangle. Similarly, for 2 points and 1 point, there's really only one fundamental geometric structure that can arise. With 4 points, there are 2. You could have all 4 points in a convex quadrilateral, or put 1 point in the middle of the other 3. With 5 points, we get the 3 familiar pictures from the happy ending problem. So for 1, 2, 3, 4, and 5 points, we get 1, 1, 1, 2, and 3 different geometric structures. This looks pretty manageable so far, but for 6 points, there are already 16 different structures, and as more points are added, the numbers grow beyond comprehension. In fact, they get so big that to this day, we've only been able to count the number of different geometric structures up to the case of 13 points. What made this such a big issue is that Dutch computer scientist Mark Overmars had shown in 2002 that the empty hexagon number is greater than 29. He found this arrangement of 29 points with no empty hexagons. Go ahead, pause the video and try to find one. With more than 29 points, the number of different geometric structures is far too big for us to even hope to enumerate, let alone search through all of them. This meant any computer program that proved there are always empty hexagons would somehow have to eliminate large chunks of cases without even checking them. At the same time, Carlos Nicolas and Tobias Gerken had proven the empty hexagon number is finite. In other words, there isn't an infinitely scalable construction with no empty hexagons, like Horton had shown for shapes with more than 6 sides. That meant we knew the empty hexagon number was greater than 29, but less than infinity. So with 29 ruled out, the search continued. Could the empty hexagon number be 30?
So a colleague here in the department, John Mackey, he was very fascinated by all the patterns that emerge in point sets. And he said not only these are really cool problems, but also people have recently been using satisfiability solvers for it. And you should really check it out. And
Professor Maren Hule and his colleague Manfred Szekeres had a stream of recent successes solving open problems with computers.
I happened to meet Manfred, and there was, this is really cool, I really like your work, and so we should team up together. And so we spent that week really working hard together on making a good start. And then I got obsessed by the problem and spent most of my summer to make sure that we were able to solve it.
Hule and Szekeres wanted to show that the empty hexagon number is indeed 30, and had several ideas of how to optimize a computer search which might be able to overcome the mountain of possibilities posed by problem number 2. But before they could even start chipping away at the mountain of possibilities, there was an even bigger issue. Remember from earlier when we formulated the happy ending problem with clockwise and counterclockwise orientations? In that example, there were 5 points to consider and 1,024 cases. But in the original proof of the happy ending problem, there were 5 points, but only 3 cases. There are clearly a lot of unnecessary cases added when we use the orientation variables. Remember, the number you see on the mountain for geometric structures with 5 points is 3, not 1024. So to deal with the mountain, Hule and Szekeres would first have to find some way to reduce the number of unnecessary cases. One thing they knew from Szekeres and Peters is that many combinations of the clockwise and counterclockwise orientations aren't actually possible. To see this, let's play a game. Here's how the game works. First, check the box in the upper right that mandates the clockwise and counterclockwise orientations of certain triples of points. The satisfied constraints are green and the unsatisfied ones are red. The goal is to satisfy them all at once by moving the points around. It's really fun. The link is in the description if you want to play for yourself.
We really wanted to have several tools for being able to visualize in real time how moving points around changes things. Changes, for example, whether a polygon is convex or not, or what the relative orientations between lots of points are.
But sometimes this game is unwinnable. For these constraints, you can satisfy 3 at a time by placing points A, B, and C in a clockwise orientation. But there's nowhere to place point D that checks all the boxes. However, this is actually a good thing. Since certain combinations of orientations are impossible, Hule could design his encoding for the computer so that many of these conflicts are quickly detected, avoiding the need to fully check certain cases. Manfred Szekeres had years earlier discovered a way to limit the search space even further. He knew that for any set of points, there exists a way of labeling those points, A, B, C, etc., such that starting from point A and going to any 2 points in increasing order of the labeling goes counterclockwise. For example, with these 4 points, ABC is counterclockwise, as is ABD and ACD. So we don't even need to consider the cases where ABC, ABD, or ACD go clockwise. The only relevant information is the orientation of BCD. This significantly reduces the number of orientation variables, and therefore the number of possibilities to check, since many orientations can be inferred just by how the points are labeled. But Szekeres found there's a weird way to order the points from left to right in addition from being ordered counterclockwise around one of the points. This turns out to be really helpful. Remember the impossible set of constraints from the game earlier? We found you can't satisfy them all at once by moving point D all around the other 3 points. But if we knew that point D was to the right of the others, we would have only tested areas in this section, allowing us to conclude our search much faster. Now, arbitrary sets of points won't actually be ordered like this. Take our example from earlier. They're in counterclockwise order around point A, but not in order from left to right. But a strangely simple sequence of transformations achieves both orderings at once without changing the orientations, which greatly reduces the complexity of searching for empty hexagons. First, move the points so that the leftmost point is at the origin. Then, for each point, take its coordinates x, y and move it to y over x, 1 over x. This makes the point at the origin go to infinity, since we just divided by an x-coordinate of 0. But that's okay, just move it back down to the upper left of everything. Amazingly, all of the orientations have been preserved throughout this process. For example, pre-transformation, BCD went clockwise, and post-transformation, BCD still goes clockwise. But now the points go counterclockwise around point A, and the very same ordering also goes from left to right. The proof that this always works involves some neat linear algebra, and you can check it out in Appendix A of Höhle and Szekeres' 2024 paper. With this transformation simplifying the cases needed to check, Höhle constructed an efficient computerized description of what the orientations of different triples of points would look like if there were 30 points with no empty hexagons. He and Szekeres wanted to show this is impossible, implying the empty hexagon number is 30. The tool they had in mind is called a satisfiability solver, or SAT solver for short. A SAT solver evaluates if an outcome, such as 30 points with no empty hexagons, is possible or satisfiable. It accounts for any combinations of the variables involved in a big logic statement. In this case, the variables are orientations of triples of points. The task of a SAT solver is notorious in computer science for being difficult to complete efficiently on complicated inputs. But the last couple decades have seen huge breakthroughs in optimizations for it.
This technology is also tested in annual competitions. These competitions started in 2002, and these competitions are kind of the driving force of the field. And every year there are dozens of solvers participating. Every year some people come up with some small ideas or some bigger ideas how to improve the technology. And every year you see problems that were way out of scope for the solvers last year can now be solved. And actually in some years we actually see big jumps.
This doesn't just allow us to answer complicated math questions. It also has major implications for many real-world problems. Now, to be clear, the newest SAT solvers are doing something very different from a brute force search through all possibilities, like we were doing earlier in this video to reprove the happy ending problem. This would be way too slow. Instead, they're making deductions about the set of all possibilities through clever choices of logically sound inferences. Given his experience using SAT solvers, Höhle thought there was a chance they could solve the empty hexagon problem. So naturally, he ran simpler experiments to gather data.
I was running the solver to see kind of what happens, and one of the nice things...
But nothing could have quite prepared him for what he saw. It was a monumental success. In one test, he reproved that the convex hexagon number is 17 in just 8.53 CPU seconds, where it had taken Szekeres and Peters 1500 CPU hours in 2005. It seemed almost too good to be true. Höhle needed to investigate further.
One of the nice things that happened over the last 10 years is that the satisfiability solvers do not only say, yes, there is a solution, or no, there is no solution, but they actually, even in the case there's no solution, they produce a proof. For most people, these proofs are practically impossible to read. But since this is kind of my field, I can read them a little bit. And so I have been looking at these proofs for smaller problems, and then I observed that the solver was discarding several triangles that needed to be empty for kind of some unclear reason to me. And so
Höhle noticed something peculiar about how the SAT solver was working. Until then, he had been testing if a hexagon was empty by checking for points inside each of these 4 triangles. The hexagon is empty if and only if all of the triangles are empty. But Höhle observed that the optimizations built into the SAT solver were frequently taking a particular shortcut, one that would unlock the secret to the empty hexagon problem with one of the most beautiful pieces of math I've ever seen.
I was really puzzled. I started to work on paper what's going on here, And then I observed that there is actually a really neat argument why you can discard some of these triangles. And although the solver was only able to come up with this argument when the points were very close together, the argument actually holds for everything. And then that allowed me to include that argument in the encoding to make it much more compact and much more efficient to solve.
The SAT solver was very often only checking this one triangle in the middle before concluding that an empty hexagon exists. That seems like it shouldn't work because there could be points in the outer triangles. But Hule realized that if this middle triangle is empty, it guarantees there's an empty hexagon. It just might be a different hexagon than we were originally thinking of. To prove this is true, think about some 6 points that form a convex hexagon. There could be more points, but right now we're just looking at these 6. If this triangle is empty, there are 2 possibilities. 1, the outer hexagon is empty, which would conclude the proof. 2, there's at least one other point in one of these triangles. Okay, say there's a point right here. Well, now we can just redraw the hexagon like so, and we're left with the same scenario as before. Either this hexagon is empty, or there's a point in one of the outer triangles. Okay, now say there's a point in this other section. But again, just redraw the hexagon and it's back to the same 2 cases. This can't go on forever, there are only a finite number of points. So at the end of the day, we eventually end up with an empty hexagon. Incorporating everything he'd learned so far, Hule's computer encoding was starting to fall into place. But as it was, a SAT solver would still need years to evaluate it. To have any chance of completing the computation in a reasonable amount of time, Hule needed to find a way to break the problem into many parts that could all be solved in parallel.
I think the first couple of weeks when I worked on this problem, this is the key thing I worked on. How can we make sure that we can parallelize the computation effectively? Because if that's not possible and it takes many years or even a century of compute, if you cannot parallelize it, it's not going to work. So I first focused...
On its face, splitting the problem into many smaller subtasks is actually more straightforward than it seems. For example, you could have one CPU check the scenario where points A, B, and C go clockwise, and another CPU check the scenarios where A, B, and C go counterclockwise. If you have more than 2 CPUs, you can even further subdivide the task based on the orientations of other triples of points. Importantly, all of these cases are independent from each other and can be checked at the same time. This greatly reduces the total amount of time needed to find the answer. For his work, Professor Hule used 1,000 small machines through Amazon Web Services, a cloud computing platform.
I took kind of some small machines, in total 1,000 of these machines, and all run them in parallel, and as soon as one finished, then the machine that becomes free will solve the next one.
With limited CPUs, it was important to choose the right triples of points to case on that would best optimize the total solve time.
So you have your big problem, and you have all these variables to assign, and I want to figure out what is the best variable such that if you split the problem into 2, one where the variable is true, one where the variable is false, that they are both equally hard, but also roughly half the time of the original problem. And this problem has thousands of variables. And it turns out that only a couple of them are really effective when you want to make this kind of split.
However, Hule found the automated tools for this in the SAT solver to be ineffective on his encoding.
There are several tools out there for partitioning. Probably the most used one is the one I developed during my PhD. But that one is highly ineffective when it comes to the empty hexagon problem. And so it has been very effective in several other problems that I solved, including the Pythagorean triples and sure number 5. But for this problem, it was completely hopeless. And it was actually making things worse.
With the failure of existing automatic partitioning methods, Hule had to go back to the drawing board and focus on methods of manual partitioning. In another fortunate turn of events, he found a good option. Experimentation suggested the most effective variables to split the problem with were the orientations of triples of points all right next to each other. This method reduced the overall runtime by roughly a factor of 2 for each split, effectively distributing the workload evenly among the CPUs. It was finally time for the moment of truth. Hule ran the solver and the wait was on. After nearly 100 years, would they finally bring a happy ending to the empty hexagon problem? Thanks to the optimizations, he didn't actually have to wait very long. All subproblems, which together would have taken almost 2 years without partitioning, were solved in less than a day. And the result was exactly what he was hoping for. The empty hexagon number was 30. Against all odds, problem number 2 was solved. The seemingly unsearchable mountain of possibilities was somehow made almost trivial by a state-of-the-art SAT solver. But there were even 2 more reasons why the fact that the proof ended up succeeding was nothing short of a miracle. Remember from earlier that certain orientations of points are impossible? Hurley was able to root out a lot of these cases with a few simple restrictions. But with more points, there are much more complicated sets of orientations that don't correspond to real sets of points. Not only that, but the fraction of possible orientations that correspond to real sets of points gets smaller and smaller. With 30 points, if you picked one possible orientation set at random, there would be roughly a 1 in 10 to the 270 chance it would correspond to a real set of points.
Kind of a rough estimation, for each assignment on 30 points that is realizable, the number of non-realizable ones are probably close to the number of particles in the universe. So this is really, it's the realizable ones are kind of such a tiny fraction.
If the SAT solver found a set of orientations corresponding to 30 points with no empty hexagons, it would almost certainly have been non-realizable, a false positive. This was a big potential issue, because it still might have been the case that all the realizable orientations produce an empty hexagon, even if there are non-realizable orientations that don't produce empty hexagons. And determining whether an orientation set is realizable or not is extremely difficult.
I have no intuition of how a human could ever realize that a set of constraints is unrealizable. If you give me a set of points with constraints and I try moving them for a while and I don't succeed, I will start sort of entertaining 2 hypotheses, right? Either I'm not good enough at, trying possibilities, or that it's not possible. And probably the more I try this and I fail, I'll be like, okay, I don't think this is possible. But I have no way of, even giving an argument. My only argument would be I tried and I failed.
By good fortune, it just so happens that even all the non-realizable orientation sets with at least 30 points produce their own notion of an empty hexagon.
Lots of assignments could be out there that are not realizable. If any of the non-realizable assignments would actually work for 30 points, then it would probably almost infeasible to make sure that we can determine it's not realizable. And if that would have been the case, then the problem would also be probably out of reach.
Another reason I found the proof so interesting is that it is monstrously long, 180 terabytes in uncompressed form. To put that in perspective, if you wrote 180 terabytes of text in a standard word processor, it would be about 100 billion pages. But the amazing thing is actually that the proof was only 180 terabytes.
These proofs can be enormous. They can be many gigabytes, terabytes, or even petabytes in size. There are lots of reasons why we can consider this a lucky solution. One of them is the search space is enormous, and any kind of brute force method would completely fail. And so you need to be somewhat lucky is that there exists a much shorter argument than brute force would produce. The other thing is that even if there's a short argument, the short argument could still be kind of 100 years of computation. That short argument...
Let me show you just how mind-boggling the number of combinations actually is. With 30 points, there are 4,060 different triples of points that could each be clockwise or counterclockwise. To naively list out all possible combinations, it would have taken an amount of memory on the order of 2 to the 4,060 bits. For comparison, the number of bits of data in the entire observable universe is only about 2 to the 265. But the 180 terabytes of proof for the empty hexagon problem is a completely negligible fraction of that, at roughly 2 to the 50 bits. The years of work on improving SAT solving technology to find shortcuts on solving large and complicated problems luckily managed to succeed on the empty hexagon problem. But despite all these improvements, there was no guarantee that it would work out.
I'm an optimistic guy, and I just want to give it a shot, right? And there's actually a range of problems that I'm also optimistic, but it never worked out. One of them, for example, is Conway's 99 graph, which also seems doable, but somehow after quite some effort, and I guess I spent as much effort on that problem as I spent on the empty hexagon, but without any success.
Besides the remarkable size of the proof being impressive in its own right, it also means something else quite unusual in mathematics. This proof couldn't have possibly been written at the time of the problem's conception. It was only made possible by massive technological advancement. This kind of computerized proof is a whole different animal, and it's been taking the math world by storm, one problem after another.
One of the first problems that we solved is when I just arrived here at CMU is Keller's conjecture. Keller's conjecture is about a tiling problem. So you have square tiles and you ask whether you can tile the two-dimensional space in such a way that there's no way that two tiles fully share an edge. If you think about it a little bit, then the only way to cover the entire two-dimensional space with equally square tiles without gaps is that tiles are placed in lanes. And so the only dimension that was still open was the 7th dimension, and we translated that problem into SAT and then solved it.
But with SAT solvers and their gargantuan proofs rising to the forefront of mathematical research, it raises a concern. A proof being terabytes in size means no one could actually read through it and verify that it's correct. So if no human can read it, how can we know for sure that it's valid? The short answer is the proof had to be formally verified with another computer program. This was done by a team of graduate students working with Professor Höhle. How it works is maybe a discussion for another video. The new trend of proofs so long that not even the best mathematicians can read them is, on the one hand, a hugely impressive milestone for mathematical progress. But on the other hand, it's a little unsettling. I mean, how can we be sure that the computer programs we rely on to verify correctness are actually correct themselves?
Who proves the prover, right? Who verifies the verifier? How do we know that the thing we built to verify our proofs is correct? If that thing is wrong, then really nothing it says matters at all.
In fact, there have been many instances throughout history where we thought a computer was doing something correctly, but later found a slight error in its logic. But at least for the case of SAT solvers, we know the automation is built upon a solid mathematical foundation.
There are interactive theorem provers. One of them that is heavily used here at CMU and various students are working on is Lean. If you want to convince the computer that it's correct, the computer is always kind of saying, no, I don't understand this. You're forgetting something. And so once you try to explain something to the computer and you finally figured out for a small problem, okay, now I convinced the computer that it agrees with me that this is true. The rigorousness with the computer, how the computer checks everything you say. And then this is just scaled to these terabytes proofs, right? They check every little detail, and as soon as anything will be missing, they would say, okay, no, I'm missing something, you need to give me more details.
While the proofs themselves might not be understandable by a human, the programs verifying them are, and we've proven that using good old regular mathematics that you and I can understand. So at a minimum, in this one instance, I think we can safely say it's a happy ending, and I think Klein and Szekeres would be delighted to know that the empty hexagon problem has finally been solved. Thanks so much for watching, and a special thanks to my supporters on Patreon and Professor Höhle and Carnegie Mellon University for sponsoring this video. If you're interested in having your research featured in a future video, please contact me through my email listed in the description below. Thanks again for watching, and I'll see you next time.